Hello everyone. In this video, I will talk about one special two-dimensional dynamics called circular motion. Now you see this circular motion, I would say almost everywhere. Now, for example, when you're driving, let's say here's a intersection of a street. And your car is here, right? And then you make a right turn. Now, this right turn can be regarded as 1/4 of a circle, right? So that is the circular motion. Now, if you're driving, let's say do a left turn, that's another 1/4 of a circular motion. So these are two examples. Now, another example would be, let's say you're looking at a highway. And you're driving this way, and then there's an exit like that. So your car will go in here and then do a circular motion with this radius. Center O is here, so your car is doing this circular motion and then exit, okay, to another street here. Or there's another kind of exit with a different radius, but let's say your car is exiting here and then go to the other direction. In the same street here. Okay, previous exit is to this downward direction, but if your car goes in here, do circular motion with this radius, little r radius, previously big R radius, and then you exit going that way, the other way. Then you have the smaller radius circular motion, okay? Now for others, like maybe it's purely in physics. So there's this loop-the-loop problem. So now let's say that's an object, right, sliding up in this vertical circle, going up like that, and then the car will go up to the top and maybe continue going. And that's called a loop-the-loop. It's one kind of classical problems that people talk about all the time. Okay, so we're going to talk about these different circular motion situations in this section of the lecture. And today we're going to focus on so-called uniform circular motion. We'll define that later on. And of course, corresponding to this uniform circular motion, there's a non-uniform circular motion. Okay, so let me label this. So uniform circular motion usually refers to this situation, that situation. Non-uniform circular motion refers to this situation here. Okay, and I will talk about the difference between these two different circular motions later on. But now, in order to describe this kind of motion, circular motion, we need a new kind of coordinate system called RTZ, coordinate system. Okay, so let me first discuss this new kind of coordinate system, and then later on we can apply Newton's laws to study them. Now here is the, so now if there's a circular motion like this, so if you look at, let's say, straight down on a circular track of an object motion, so let's say object is moving with some velocity v, okay, like this, then we know the object will go around the circle. But now, if you look straight down, then you will see a circle, right? The object is moving in the horizontal direction. But now imagine you're looking this way. You are viewing from this horizontal angle. Then people usually draw a picture that look like this. It kind of turns into an oval shape. The circular shape, if you view from the side, usually becomes kind of like an oval shape. And then we're going to use this angle here because it's easier to draw the coordinate system, the RTZ coordinate system from this angle. Okay, so now let me draw the RTZ 3 directions. So here's the center of the circular motion, and then the object is here. Now the R direction refers to this radial direction. And I'm going to use a unit vector called R hat to represent this radial direction. Now the object is moving right now along this, its velocity is along this tangential direction. Okay, so let's draw this tangential direction called a T hat. Okay, but let's also the direction in the vertical direction. Okay, so it's the direction that we look straight down, that direction. That's called its Z hat. Okay, so let me give them some definition. Actually, let me redraw this T hat direction. It's too similar to the vertical direction, and I don't like that. So let me draw a tangential direction along that direction, T hat. Okay. But again, remember, T hat, the direction here is along the tangential of the oval trap, of the circular trap, sorry. The circular track, a better drawing will look like that. Okay. All right. So let me write down these 3 directions: R hat, radial direction, and that direction is toward the center of the circular motion. T hat is tangential direction. It's the I forgot to mention they're all unit vectors. Right, it's the unit vector along the tangential direction. And in terms of physical quantity, that would be velocity. Okay, so along the velocity direction. And it's perpendicular to the radial. Now the third direction is z hat. The direction here, remember we mentioned that it's the direction perpendicular to the circular track. Okay, so perpendicular to the circular track on the circular motions 2D plane to the motion plane. It's perpendicular to the motion plane. Okay, so these are the three unit vectors definition. Now, you may say, why do we need this coordinate system? Isn't x and y already enough? So let's say I build inside this two-dimensional circular motion plane and x and y coordinate. Okay, the answer is yes, you can do that. However, in that case, you will need to discuss ax, ay, and they both always changing with the position of the object, and it's not very convenient. Okay, so you can still do this, but the point is that it's not convenient. And you will also miss the effect of radial A and tangential T. So you miss the point of separating these two acceleration. They will separate. Separate the effect of acceleration A. Okay, so remember we talk about the relation of V and A in 2D. Okay, so we said that let's say there's a velocity V and an arbitrary acceleration A. Okay, and we want to decompose A into perpendicular direction to the velocity and parallel direction to the velocity. We want to separate them, decompose them into these two directions, and then the effect of A parallel is to either speeds up or slows down an object, right? So meaning that it changes with magnitude. Okay, and the effect of the perpendicular component is changes velocity's direction. Okay, so remember that we talk about speeding up, slowing down, and turning right or turning left. Turning right or turning left is the changing of V's direction, the velocity direction. So we separate that into the two components. Now that's exactly what we're doing here. The A parallel component will be the same as this tangential component. Okay, so these two are actually the same. And the perpendicular component of the previous discussion is actually the radial component. they're the same. Okay, so we're building this RTZ coordinate system just to accommodate that kind of decomposition of A, so that it's easier to separate the effect of A into these two directions. Okay, so again, X and Y Cartesian coordinate system is not very convenient to study the circular motion dynamics. Okay, so now with this circular motion dynamic with the new coordinate system, RTZ coordinate system, we need to write down along these three directions Newton's laws. Okay, so so what happens in the R direction? Let me quickly redraw that coordinate system, and then we can write down these three equations. Okay, that's it's R hat direction, it's the tangential direction, and that's the vertical direction. Okay, so in terms of Newton's laws, Newton's second law should be applied to the radial direction. Along R hat direction, we should have the net force along this direction should be non-zero, right? Because otherwise, the object's motion will not change its direction. But we know that the object is doing circular motion, so it's constantly changing its direction. So that means that the net force along this radial direction should not be zero. Okay, so we should write down whatever force that we have along this direction equal to MAR. Okay, and it should not be zero. Now along the tangential direction, we should have also Newton's second law, but now the question is this net force zero or non-zero? Okay, so we're going to separate into two different situations. The first one is the uniform circular motion. Then, of course, we should have zero here for AT, and that defines uniform circular motion. Because in this case, the velocity is constant in magnitude, or you can say the speed is a constant. That's what we call uniform circular motion. So the speed does not change, or velocity's magnitude does not change. Now another situation here we're going to talk about in a second video next time will be non-zero here for AT. Okay, so that defines non-uniform circular motion. And in that case, the speed is not a constant. The speed can change during the circular motion. Okay, so again, the tangential direction defines the uniform or non-uniform circular motion. Now, how about the z-hat direction? The direction perpendicular to the motion plane. And in this direction, we can be sure that it's always zero. So whatever force we have here should be zero, right? Because otherwise, if this net force is non-zero along the z-hat direction, then the object will fly out of the plane, either going up or going down. Okay, so that's not the situation we're going to discuss here. We're discussing 2D, okay, because that's the our basis for discussion here is a 2D motion, not 3D. not 3D motion. Okay, so that's why there's no acceleration along the z-hat. All right, so now we can proceed to talk about uniform circular motion dynamics. And to talk about that, I want to use two examples. The first example is the a car turning the corner. So that's the example I talked about earlier. This example, so let's say there's a car, right, driving this way with a constant speed, and then turns the corner, and this part of the trajectory is circular with radius r. Okay, so now the speed here is v equals a constant. Okay. All right, so now first let's draw the free body diagram for the car during the turn. And again, it's hard to draw the diagram in this angle. So let's imagine that we're looking at the circular motion from this horizontal direction. Okay, we're viewing along the horizontal direction. Then I can use this kind of picture. Then the vertical direction will be this direction, right? Because we're viewing horizontally. So here's the ground surface. That's the ground, okay? So the normal force due to the ground will be upward. Gravity will be downward. Suppose mass of the car is m. And we must have some force in this horizontal direction so that it can go around a circle, the point O, right, in a circular track. So that means that we need a force in this direction, in the radial direction. And that is the friction force, Fs. Okay, so when a car turns a corner, the force that makes this happen is the static friction. All right, so now how exactly can we write down these three directions, RTZ, along RTZ direction? So let me put the RTZ coordinate system on, okay? So R should be along this direction. That's R hat direction, okay? And then the car is going that way, so the tangential direction is like that. And then the Z direction will be this vertical Z hat. Okay, so now let's think about the radial direction first. The net force along radial direction is simply just the static friction Fs, and it should be equal to MAR, okay, radial acceleration, AR, or sometimes people call it centripetal acceleration, AC, okay, they're the same. All right, now in the tangential direction, there's nothing, right? Because the car here is moving with a constant velocity, right? So we should not have any friction force along that direction. Okay, so friction force is totally along the radial direction. So again, nothing here. And along the Z hat direction, there's this normal force, which is positive along the positive Z hat direction, so it's positive. And the gravity is downward, so it's negative. And they must cancel each other so that we get 0 here. So the car is fixed on the ground, it's not flying up. Okay, Okay, so that's the equation we should write down. And then usually the question will ask you what is the, let's think about this problem. What is the maximum speed, Vmax, that this car can use to turn a corner? Okay, so what's this Vmax? Now for that kind of problem, we need to continue here with this equation by replacing, replacing a by AR by V squared over the radius R. Okay, we need to do that. And if I need to talk about the maximum speed, then I need to think about the maximum static friction. Okay, so when the friction force is maximum, then the speed here will be maximum. Okay, so let's replace this Fs by Fs max, and then this V here is V max. All right, so think about what is this value here. So we should write down one more equation. Yeah, excuse me. So Fs max equals mu s times n, right? So that's the equation we discussed in the beginning of the chapter. We talk about the different type of forces. We talk about the static friction, and then the maximum static friction is given by mu s static friction coefficient times the normal force. Okay, now from this equation, I know n equals mg, right? So it's mu s mg. Okay, because n is unknown, so we're going to get rid of this normal force n first. And that will go in. So after this, we want to plug in this equation, this expression in the first equation. Okay, so let's see. We have mu s mg equals m V max squared over R. Okay, now the 2m cancel out, and V max equals square root mu s gr. Okay, so that's the V max expression we get from the static friction, friction coefficient, and the gravitational constant g, and also radius r of this street. Okay, and let's do some estimate. Now suppose we're looking at a very good tire, so mu s is almost 1. Okay, and the g here, right, is almost 10, right? 9.8 is like 10 meters per square second, and radius r, let's say for a small street, is about 10 meters. But it's probably greater than 10 meters. I just want to use 10 meters as a convenient number to do the estimate. Okay, so we're going to estimate this V max equals square root 1 times 10 times 10, and that equals 10 meters per second as the speed. So maximum speed is about 10 meters per second. Okay. All right, so let's translate into miles per hour. It will be about like 22 miles per hour. Yeah, something like that. Okay, so that's like the speed limit. okay, for a small street. But of course, when I said that 10 meters for a small street, probably is still underestimate. Usually, even for a small street, radius is greater than 10 meters. 10 meters, okay? Okay, so that's one example of uniform circular motion. Now let's talk about another example of uniform circular motion. It's called a banked surface. Okay, so now let's see one example of the banked surface. It's also in the opening discussion I made earlier. So let's say there's a highway and there's a car driving this way, and then you want to exit highway like this. So there's a ramp going like this, and the car is doing circular motion inside this ramp. Okay, and if you look carefully, the surface of this ramp here, you will see it's banked. So the side closer to the center is lower than the side further away from the center. So you will see some kind of surface that look like this. Here the dashed line is the horizontal direction, and that is the surface of the ramp, look like this, and the cars here, okay, driving on this banked surface. That's called a banked surface. And usually we have an angle to represent the grade of the surface. So there's an angle theta with horizontal. Okay, and the car here, okay, is driving along this circular path with radius r. Okay, so let's also label this radius r. Okay, so in reality, the car is like a spiraling down, right? Spiraling down the surface. It's not in the horizontal direction, but we're simplifying this situation. We're talking about the car here doing circular motion in this horizontal plane. Okay, so let's see. I can draw its trajectory like this. Okay, so the car is doing circular motion with radius r, but the car is doing that on this banked surface. Okay, so that's the situation we're going to talk about. Now first, let's draw the free body diagram. Now on the surface here, there must be a normal force perpendicular to the surface acting on the car. And there must be gravity in a vertical direction. Okay? And there must be a friction force. Actually, we cannot say that right now, because the friction force depends on the car's tendency. We know it's static friction, but we don't know the direction of it. So that's why I cannot draw it right now. We need some more conditions. So let's put in some more conditions here. So now let's say the car right now is driving at a proper speed. Let's call this proper speed VC. Okay, so that there is no static friction on the car. Okay, so in that case, we don't actually need to draw the static friction. There's no static friction at all. Okay, so now let's see, can that happen? Is that possible? The answer is yes. If you write down the dynamics along the RTZ direction. So here's the R head direction, okay? And the T head will be that tangential direction. Now the Z head is this vertical direction, okay? So we can write down sigma F R. In this direction, we get MAR, which is MV squared over R, okay? And along the T head direction, there's nothing. Along the Z head direction, we have the normal force, right? And then the gravity. Yeah, so sorry, I forgot to write down the net force in the radial direction. So let me write down now. So we have this normal force, right? But the normal force is not along the R head direction or the Z head direction. In fact, it makes an angle. So this angle with the Z head is angle theta, the same as this banked angle of the surface. Okay, so that's why we write down the sine component and sine theta for the radial direction. And that's it. Gravity has no component because it's perpendicular to the radial direction. Now along the Z head direction, the net force should be 0. So sigma Fz should be 0, but it's given by n cosine theta, which is positive. Gravity is negative, and it must be 0 here. Okay, so that's why we can calculate the proper speed Vc. Since we use Vc there, so let's call this Vc, and let's figure out what is Vc, so that there's no static friction. Now, from 2, we get normal force equals mg over cosine theta. Now let's substitute into 1. We have normal force times sine theta equals mg cosine theta times sine theta equals mvc squared over r. Okay, now from there I can solve for the Vc. So Vc equals square root, by the way, the 2 m's cancel out, okay? And sine theta over cosine theta becomes tangent theta. So that's why we have gr tangent theta. That's Vc, okay? So that's the proper speed when there's no static friction. Okay, so now we figure out this speed, and it's possible. So if you're driving right at this speed, you'll feel most comfortable. That's the most comfortable speed for passengers. And the reason for that is because there's no tendency for the passenger to slide either left or right, right? Because there's no tendency to slide, no tendency, no static friction. So that's why it's the most comfortable speed. But in reality, when you drive in the ramp, you'll probably not at least speed. It's like a single point, you cannot hit that, right? So you should be sometimes greater than we see and sometimes less than we see, and that will be the basis for the next discussion. We're going to talk about static friction. That's when the static friction comes in. Okay. Hello everyone. In this video, I will talk about the non-uniform circular motion in two dimensions. Now first, let's review what constitutes a non-uniform circular motion. Now in the RTZ coordinate system that we discussed in the previous video, let's say here's the circular motion center, and then the radial direction points toward the center. That's the tangential direction, and then there's also this z-hat direction perpendicular to the 2D plane. And we said that we should have the following. Along the radial direction, there's some net force sigma Fr equals MAR, which is given by mv squared over r. Okay, so let's say radius is r here. And along the tangential direction, the net force now should not be zero. It should be something that give rise to the AT. Okay, so equals MAT, and the non-uniform circular motion condition is AT is non-zero. Okay, so we should have some net force along this tangential. Now along the z-hat direction, we should still have a zero here. So there may be some force along this direction to balance each other. And that is the conditions or equations for the non-uniform circular motion. Now, under such a motion, the speed, of course, is not a constant anymore. The speed of the object will change throughout the circle. And that is actually implied by AT non-zero. Okay. All right, so let's look at one concrete example of this non-uniform circular motion. And I'm going to use this vertical circle. Okay, so here the circular path is along this vertical direction, and the radius of the circle is r. And then there's an object, suppose, for example, it's let's say a small block, okay, sliding up. And the surface here is smooth. Meaning that there's no friction to consider. All right, so now let's draw the free body diagram. The surface of the circular track should apply a normal force along this radial direction, and gravity should be in the vertical direction. And since the surface is smooth, so there's no static friction or kinetic friction. And that's it. That's the free body diagram. Okay, so let's write down the let's build the RTZ coordinate system and then write down the three equations. R direction is along this radial, along the normal direction. Tangential direction is this way, tangent to the circular track. And then the z-hat direction will be in the horizontal direction. So I cannot draw it because right now it's vertical to the screen, right? So I can say z-hat is perpendicular to the screen. And in fact, we don't need to worry about this direction because both normal force and the gravity are inside the plane, so they have no component of their forces along this direction, along the direction perpendicular to the screen. Okay, so another way of saying that is when I write down that equation along the z-hat direction, there's nothing there. Okay. All right. So now along the along the r hat, along the radial direction, the net force equals the normal force is already along that direction. So let's write down normal force first. Now the gravity here, okay, has some angle with that direction, and I'm going to use this angle here. So let me first extend the radial direction, okay, and this angle, I want to call it theta angle, is the same as this angle theta. Okay, so now we need to consider like how to describe, how to introduce this angle theta. So now let's say when the object, when the block is here, the angle is theta equals 0. So that's likely angular displacement is 0. Equals 0 at this instant, and then later on at instant t, so that's t equals 0 second, we have theta equals 0, and then at instant t, we have theta angle, and that's this angle here. Okay, all right. So now with that, when I look at the gravity's component along this radial direction, it will be mg cosine. Okay, that's the cosine component of mg. And it's negative because it's opposite to the r hat. And that equals mar equals m v squared over r. That we want to calculate later on. Okay, now along the t hat, the net force equals, okay, so now we need the mg sine component, and that is negative. Okay, because the t hat direction is pointing along the increasing angle direction, right? Theta increases along this direction, and that is defined as positive direction, and then the gravity is pulling it down, so it's in the decreasing theta direction, so that's why it's negative. And that equals mat. All right, and so how to these are the two equations we have, and then now the question is how to solve at least the velocity information. What is the velocity? In terms of the velocity, we can say if I can find v equals vt, then that's good. But it'll be hard here for this problem. So we're going to just solve for v equals v as function of theta. So let's say we identify the angle theta for the block, and then if we plug in that theta, then we know its speed, and then that's also good. Okay, so let's try to find this expression. Now to do that, I want to do something here. I want to rewrite at as dv dt. Okay, so that's our definition of the tangential acceleration. It will change the magnitude of the speed of the velocity, sorry, and so that's why it's dv dt here. Now with that, I can I can do some integral here. So I want to integrate out the v, and then I want to integrate out this time or the angle. Now time would be difficult, so let's try to integrate out the theta here, the angle here. So what we have here is dv dt, and let me rewrite this as dv dv d theta and then d theta dt. Okay. Now the theta here, if I move it to the left side, then I can do the integral of angle theta. However, I introduce this d theta dt, so let's think about this first. D theta dt is omega, right? It's angular speed. But we also know that there's a linear speed and angular speed relation, omega equals v over r. Okay, so now if I apply that, I can change the variable omega to the linear speed v here, so that I can do the integral. Okay, so now I can let's cancel the mass first, and then I want to move the d theta to the left side together with the r here, and that's d theta, and the right side is v dv. Okay, now I can put an integral sign on both sides, and we need to certify that the correspondence is correct. So for example, at t equals 0 second, we can say the speed here is 0. Okay, so I'm going to start from 0 here. Oh, sorry, not 0. Some initial speed cannot be 0 because the block need to slide up. And at this instant, we have v here. Okay. Now for the angle integral, right, at t equals 0 second, the angle is 0 radian. And then right now it's at theta angle. So that's the integration bounds. Okay. Now let's see. The sine integral becomes cosine, right? Becomes cosine. But there's a negative sign, so we need to absorb that. So it's gr cosine theta. Theta goes from 0 to theta equals 1/2 v squared. So let's plug in the lower and upper bounds and then see what we get. So we have gr cosine theta minus 1 equals 1/2 v squared minus v naught squared. And if I rearrange these terms, I will get v squared equals v naught squared. So you need to move the v naught squared to the left side, so it becomes positive. And then we already multiply 2 on the left side, so plus 2gr cosine theta minus 1. Okay, so a bit of discussion here. So at any angle theta, this cosine theta becomes positive, right? Becomes positive, and it's less than 1. So this subtraction here, cosine theta minus 1, is negative. So you get a value of v less than v naught squared, right? So at any instant, it's less than v naught. So that's reasonable because the when the block slides up, it slows down. Okay. Now in the future, we'll also see that this equation is the same as the mechanical energy conservation. If we apply that, we'll get exactly the same equation. Okay. All right. So that's the one example of the non-uniform circular motion. And then we can actually talk about in detail the object's motion here. And right now it's like an arbitrary position. Now let's focus on some special positions. So again, here's the vertical track. And what are the special positions? So I'm going to talk about the bottom, the top, okay? These two positions. And we're going to study the requirement for the block to reach the top point. Okay, so that's the top, bottom. And then we also talk about at a position say here, the block falls off. Okay, so let's call this falling off position. Let's try to find this angle. So let's say the horizontal direction is this dashed line. Now what's this angle here? When the object, the block falls off. Okay, so let's talk about these three special positions, and then we'll be done with the non-uniform circular motion. Now at the top, first we need to draw the free body diagram. So I'm going to draw it here. So the normal force, the contact surface between the block and the track is above the block. So the normal force is going to push down the block. The gravity is already in this direction. Okay, now this direction is also the radial direction. Okay, and then there's nothing in the t hat tangential direction or the z hat direction, so we don't need to add to draw those directions. Now let's write down the Newton's second law along the radial direction here. So we have normal force plus gravity equals MAR. Let's also replace AR by V squared over R, so that's radius R. Okay, and then that's it. And then we want to find a special speed or the smallest speed, V minimum. What is this V minimum? So that V minimum, so that the block stays. The block can reach the top position. All right, so under that condition, we have normal force equals 0 at V minimum. Okay, so meaning that there's no pressure between the block and the track. So that's the signal for normal force being 0 here. Okay, so now with that, I get mg equals V minimum square over R. So V minimum equals square root of GR. Okay, so now figure out the minimum speed we need for the block at the top, so that it can reach the top without falling off. Now the bottom. Again, first the free body diagram. The normal force is upward now. Gravity is downward. And the radial direction is around the normal force. So that's why when I write down Newton's second law, I have normal force minus mg equals MAR mv squared over R. Okay, so now we don't need to talk about the such as minimum speed or maximum speed, because none of that will make the block falling out the track, right? So we just need to, for here, we just need to calculate normal force. So equals mg plus v squared over R. Okay, so now we can see, because v squared over R is always positive, so this term is always greater than mg. So when the block goes past the bottom of the loop, the normal force is greater than gravity. So that's the gaining weight. One example of this experience would be, let's say there's a car going over the bottom of a valley, let's say. Then the passenger inside the car will feel gaining weight in this process. Okay. All right, so let's talk about the falling off position. Falling off angle. How can I find this angle? Okay, so again, we need to draw the free body diagram. Remember, free body diagram is always the first step. Okay, so I'm going to draw first the normal force. That's along the radial direction. And gravity is this way. Sorry. And as I drew earlier, that's the radial direction. Okay. And then the angle here, that's the angle we're looking for, right? Now, to translate that into the angle that we need here to do the decomposition, let me first draw the tangential direction. Okay. Now this angle is theta, means this angle is theta. So you can write down the Newton's second law in the radial direction. It's given by normal force, the sine component equals MAR equals MV square over R. During the process of falling off the track, the normal force should be 0, right? So that's the condition that we must have here. Okay, so what we have here is mg now sine theta equals m v square over r. So that's the falling off speed. Square root of gr sine theta. Okay. Okay, so that's the falling off position theta, its relation with the speed at this falling off position. So now notice that the speed is not 0, right? It's not 0, so it's something finite. Now in the future, when we talk about this falling off position, again, using the energy conservation, then we can exactly calculate this angle. Okay. All right. So that'll be all for this video. Thanks for watching.